In a sealed vacuum chamber, a droplet of molten tin falls through darkness. A laser finds it, flattens it, then strikes again, and the metal detonates into plasma hotter than the surface of the sun. A pulse of invisible light erupts outward. 50,000 times every second, this tiny explosion repeats. To understand why anyone would build such a thing, start with something ordinary. A polished disk of silicon, mirror bright, the width of a dinner plate. Onto its surface will be printed billions upon billions of switches, each far too small to see. Everything you call modern begins here. A transistor is simply a switch with no moving parts. Feed it current and it opens or closes, 1 or 0. Stack enough of them, wire them together, and you get arithmetic, memory, language, intelligence. The entire digital world is that one trick, repeated at unimaginable density. In 1965, Gordon Moore noticed that the number of components on a chip was doubling at a steady pace. It was an observation, not a law of nature, but the industry turned it into a promise and then spent 60 years and hundreds of billions of dollars keeping it. Keeping it meant mastering one process above all others: photolithography, printing with light. A patterned mask is illuminated, the image shrunk, and projected onto a wafer coated in light-sensitive resist. Wherever light lands, chemistry changes. Etch away the rest, and the pattern becomes circuitry. But light has a limit. You cannot print a feature much finer than the wavelength you print with. For decades, the industry pushed downward, ultraviolet, then deeper ultraviolet, until it arrived at 193 nanometers and stopped. There was nowhere obvious left to go. Engineers found tricks. They flooded the gap with purified water to bend the light harder. They printed one pattern, then a second offset beside it, then a third, building fine structures from coarse ones. It worked, but every extra pass added cost, time, and another chance to fail. There was one alternative, and it was almost absurd. Skip the incremental steps entirely. Print with light of 13.5 nanometers, extreme ultraviolet, a wavelength roughly a fraction of 1% as long as visible light, measured in a span only dozens of atoms wide. The problem is that extreme ultraviolet light barely exists in our world. It is absorbed by almost everything it touches. Air swallows it. Glass swallows it. There is no lens on Earth that can focus it. To use this light at all, you must build a machine with no lenses and no air. So, instead of lenses, mirrors; instead of atmosphere, vacuum; and instead of a lamp, an artificial star, created and destroyed tens of thousands of times a second. Every element of the machine follows from that one impossible choice of wavelength. Nothing about it is conventional. The effort began in research labs in the 1990s. American national laboratories and a consortium of chipmakers proved the physics was possible. Turning physics into a factory tool fell largely to one company in the southern Netherlands, and it would take them the better part of 30 years. Veldhoven, a quiet town near the Belgian border. Low buildings, flat farmland, gray Dutch skies. There is nothing here that looks like the center of the world economy. And yet every leading-edge processor on the planet is printed by a machine that was born on this campus. The machine they built is roughly the size of a shipping container turned showroom. Tall enough to need a walkway, heavy enough to need reinforced floors. Around 100,000 individual components. Kilometers of cabling and hosing. Parts drawn from thousands of suppliers across dozens of countries. It begins with tin. A generator releases droplets of molten metal, each roughly a fraction of the width of a human hair, falling in a precise stream through vacuum. Around 50,000 droplets every second. Each one is a target, and each one must be hit exactly. Each droplet is struck twice. The first pulse flattens it into a thin disk, spreading the metal out. Microseconds later, a second, far more powerful pulse slams into that disk and blows it apart into plasma. Only in that instant does the tin radiate the light the machine needs. That plasma reaches temperatures in the hundreds of thousands of degrees, far hotter than the surface of our own sun. It exists for a heartbeat, radiating extreme ultraviolet in every direction. Then it is gone, and the next droplet is already falling into place. The laser doing the striking is itself a monster, a carbon dioxide laser system filling much of a room. Its beam amplified in stages and steered along a carefully guarded path before it ever reaches the droplet. Most of that energy is lost, only a sliver becomes useful light. A curved collector mirror sits close to the plasma, gathering the light that sprays outward and folding it into a beam. It works within reach of an exploding star and a rain of vaporized metal. It is a consumable part in a machine that costs more than an airliner. From there, the light enters the optics, mirrors ground and polished in Germany, and among the flattest objects ever manufactured. The standard comparison is stark. Scale one of these mirrors up to the size of a country, and its largest bump would still measure less than a millimeter. Even perfect smoothness is not enough. No material reflects extreme ultraviolet well, so each mirror is coated with dozens upon dozens of alternating layers, only atoms thick, that reinforce the light instead of absorbing it. Even then, roughly a third of the light is lost at every single surface. Count the reflections: the collector, the illuminator, the mask, the projection optics, and roughly 10 surfaces stand between the plasma and the wafer. By the end, only a small percentage of the original light survives. This is why the source must be so violently, extravagantly bright. The pattern itself lives on a mask, but not a transparent one. Because extreme ultraviolet is absorbed by everything, the mask must also be a mirror, its circuit design etched into a reflective coating. The light bounces off it, carrying the blueprint of a chip toward the wafer. The optics then shrink that image, projecting a pattern several times smaller onto the resist below. And the wafer does not sit still. It sweeps beneath the beam while the mask sweeps above it, the two moving in perfect opposition, field after field, across the whole disk. Those stages accelerate hard, reverse, and stop, thousands of times an hour, yet must hold their position to within a few billionths of a meter. Magnetic levitation replaces bearings. There is no rubbing, no friction, nothing to wear. Only fields, holding a moving mass in midair. At this scale, everything is noise. A truck passing outside, a change of a fraction of a degree, the heat of a human body through a wall. So the machine is isolated from the ground, held to fractions of a degree, and constantly measured against itself by interferometers, reading distances finer than an atom's wick. Every layer must land on the one beneath it. A modern chip is dozens of patterned layers stacked in sequence, and a misalignment of a few nanometers ruins the whole wafer. The machine measures, corrects, and remeasures continuously, printing more than 150 wafers in an hour. Shipping one is an operation in itself. The system is broken into modules, packed into dozens of freight containers, and flown out on multiple cargo aircraft. At the customer's fab, teams spend months reassembling and calibrating it before a single production wafer is exposed. Running it consumes power on the order of a megawatt, a small town's worth of electricity for one tool among hundreds in a fab that may cost tens of billions to build. And still, the economics work, because there is no other way to make these chips at all. The chips it prints end up everywhere, in phones, in cars, in medical scanners, and above all, in the racks of accelerators now training artificial intelligence. A single machine's output, multiplied across years, touches a substantial share of the computation happening on this planet. The next generation goes further still. Larger, more steeply curved mirrors gather light at a wider angle, sharpening the print. The optics become asymmetric to compensate. The machine grows to roughly 150 tons and a price around $380 million, and the first units have already been delivered. One company makes these machines, no one else. That fact has moved lithography out of engineering and into statecraft. Export controls, national subsidies, treaties over tools. A device designed to print circuits has become one of the most closely guarded objects in international politics. It is worth sitting with what this actually is. Molten metal exploded by light, mirrors polished to the scale of atoms, vacuum standing in for air. Thousands of companies, 3 decades, one shared goal: to draw lines too small to see. The invisible world we now live inside was printed, one flash at a time.